right, we are in AP Calculus. Today's date is Tuesday, February 25th, 2020. We just had our Alice drill, and it was slightly unpleasant, to say the least. It was cold and hot at the same time. I don't know, it was cold wind, and then the sun was warm. I don't know. Integral analysis. Objective, determine what is happening when you're taking the integral of a graph. Everything today is about the graph, so we might as well talk about the graphical analysis. These are things that you should have memorized. These left two columns are the f prime test, the first derivative test. This right column, I guess I should be moving this a little bit more to the right. This right column is just the second derivative test. What is the definition? You should have these memorized. Ready, set, arrow. Definition, f increasing. F prime is greater than 0, yes. Claire, f decreasing. Stego, f critical value. And, yep, or I guess I should say, or f prime d any. Essentially, set the top and the bottom of the fraction equal to 0. That's the shortcut for finding critical values. Geo, f relative extremum. You said it for this last one, so you can say it again.
F prime. F sign change. There you go.
There it is. Sign change. Arrow, F minimum. There it is. Sign change from a negative to a positive. Claire's always getting these easy ones. F prime goes from where to where for an F max?
Positive.
There it is. F concave up, arrow. No, wait, sorry. We're going to stego. I don't know why I went back to arrow. Stego, F concave up. First of all, it's what prime test? Double prime. So F second prime. Second derivative is, it's kind of like this first column. Greater than 0. Geo, F concave down.
Less than 0.
F double prime less than 0. And F inflection point, we'll give it to Claire because she didn't get a hard one yet. There it is. F double prime sign change. All right, so if you don't know those, practice them because you should definitely have them memorized. All right, so these are the types of integrals. It's kind of expanding on yesterday's lesson. So an indefinite integral, that's the first antiderivative that I ever showed you. That means I'm going and taking the antiderivative out from negative infinity all the way out there to positive infinity. I'm taking the antiderivative of the entire function. So I don't know. I'm going to just draw some random curve with arrows, or Claire's as we're calling on this class since we have a
Oh my god.
person named Arrow. This goes on and on forever in both directions. So if I'm talking about the area between the curve and the x-axis, we would say that this has infinite area. I guess if it was a sine wave, it kind of converges. Well, it doesn't actually converge, but it never goes out to infinity or negative infinity. It's bounded by a certain amount depending on what type of sine function you have. And then you've seen this before. The antiderivative, we just write that with an integral symbol with no beginning and end, no start and end, of just, I don't know, we'll call this f of x. Say this function is f of x. So the antiderivative of f of x is we'd have to do f prime in order to find the f. So we'll do like f prime of x dx. All right, let's draw the same-ish function again, but this time you can even do Claire's on the ends of this function. But this time, a definite integral, I care about, ooh, what just happened there? No, go away. There it goes. I only care about a certain part of this graph. So this obviously has a finite area, or a definite area, and that's from usually a to b. So what does our integral look like? Someone. A to b of f prime of x dx. And again, we're assuming that this is a function f prime of x. Perfect. And then accumulation. So this is more formalized, but it's kind of cool. So again, draw your same function with your Claire's at either end. And accumulation is interesting. So let's go back to the integral that I talked about yesterday. Yesterday I said an accumulation integral is the integral from some number. I'm going to call it a. A is a number, like 0, 1, pi, I don't know, some number, but we don't have an end. I'm going to call this x. We'll call this f prime, I can't say x because it has to be a different letter, I'll say f prime of t dt. That means that this function now is now f prime of t. We have a start. So just like we have a start on our definite integral, we have a start on our accumulation, we have a bar here from a. But it keeps on going forever and ever. There's no end. I can choose whatever end I want. I can choose how much area I'm talking about. I could have like, I could come out to x1, I could come out to x2, I can come out to, that's not a 2, I can come out to any x value that I want. And that will change the size of the area that I have. We're all understanding what's happening in terms of an accumulation integral in terms of its graph. All right, lots of head nods. I'll take it. So, derivatives of accumulation functions. So, generally the way that they're going to be given to you, they're going to say, a function is equal to an integral where I have a number down here and a variable up here of some function. What you're going to be doing with today, in order to take the derivative, you take the derivative of both sides, right? So, d dx, the derivative with respect to x of the left side, the derivative with respect to x on the right side. What's going to happen here? What happens? Yeah, so we can say down here that this is, we'll call it just g prime. G prime of x. And Claire, you have it. Yeah, it's just you cancel it out. So this is now f of the derivative and the integral symbol cancel each other out, and this is f of, is it t or x, Claire? It's actually x now.
What about the a?
Oh, that's a great question. I'll answer that on the back. What happened to the a? But there it is. So how does that work, though, Mr. Sindel? Well, technically, it works like this. And I guess I can partially answer it right now, but I'm going to have a more formal definition in the back. When I take the derivative of something that's definite, obviously the integral of lowercase f is, you guys all know this, it's, there it is. Yeah, say it louder. Capital F, right, yeah? Yeah, so it's I'm just looking at this guy. I'm not taking the derivative yet. The antiderivative of lowercase f is capital F of t. Now evaluation bar between a and x. And again, we always assume that a is a constant, some number, not a variable. Okay, well, what is capital F of t? That's going to be capital F of x minus capital F of a. Yeah, so you can see it already. d dx. I'm taking the derivative of that thing that I just found, capital F of x minus capital F of a. I'm kind of answering Arrow's question here. This is pretty formal. I'm using variables. Well, f of a, again, if I'm plugging in a number into a function, I should pop out a number. So this right here, you can make a note to yourself. You can call that the constant term. I like using the hashtag or the octavar. That's just a number. So the derivative of a number is 0. The derivative of a constant is 0, which means this derivative is really just the derivative of capital F of x, and the derivative of capital F of x goes back to lowercase f of x. So that's where we get lowercase f of x, and that's where we got right up there, what Claire stated from the very beginning. And just as a note, in case we forgot, the integral of lowercase f of x turns into capital F of x in terms of just calculus notation, and then the derivative of capital F of x turns into lowercase f of x. These two mean the same thing. So if you ever see these, you're like, oh yeah, okay, they're just using that same definition.
Except for when f, because remember that was that one problem when I thought that lowercase f of x, you could use this rule and it was like not
I'm trying to remember. I vaguely remember that, but if you ever see a capital F of x, you'll know what the definition is. And you had a capital F of x?
I think I had a lowercase f of x.
Okay, yeah, so you can assume it only if it's formally defined somewhere. So you can define also if it's not written already.
Yeah.
All right, so the backside. Let's be kind of formal about this. So we have already seen what happens. If I take the derivative with respect to x of this thing, Claire defined this, so Claire can't say it again. Do you guys remember what this is? I just wrote this again, the same thing that we had on the front side. Well, we defined it as g of x, but yeah, what is this though? What is g of x? F of x. This is our second fundamental theorem of calculus. But there's a chain rule that you're not seeing. It's hidden in the background in the shadows. You will not see this chain rule 75, I'm just putting a random number on that, percent of the time. Normally, you're not going to have to worry about that. But if you're in BC Calculus, which now all of you are, you will be seeing it a little bit more now, maybe 50% of the time. So what is the chain rule? The chain rule looks like this. What we're really doing back here is we're just plugging in the x right there. And there we have that f of x. We see we're just kind of plopping it in. We're substituting it in. What's actually happening is this. We want to say, yeah, so this v is put in there. So f of v, just like before, is going to be substituted in, but then we're also going to multiply by whatever the derivative of whatever that is. What is the derivative of v? I'm going to call it, I don't know, dv dx, I guess, of v prime, whatever you want to call it. I'll call it v prime. And because it's a definite integral, I'm going to subtract what happens when I plug in this guy. So I'm going to say, okay, I'm going to plug in u in this case. So this is going to be minus f of u times, guess it, u prime. Yep. And check this out. Let's apply that to the problem that we just had up above. What is the derivative of a again? The derivative of a constant is always 0. The derivative of a constant is always 0. Therefore, 0 times this, the second part doesn't exist for most of the time. If this is ever a constant term, we don't have anything to subtract for a definite integral, which means we're only left with this original thing. And if this is a variable like 2x, or sorry, just x, if it's only x, then the derivative of x is always 1, which means I just plug it in. But if I have something else like x to the power of 3, then weird things are going to happen. I'll show you. So let's try the chain rule on the second fundamental theorem of calculus, example 1. What am I going to do? Yeah, that x cubed is being plugged in here and here. So this is now going to be not t squared, but x to the power of 3 quantity squared plus 2, not a t anymore, but x to the power of 3. Okay, let's put parentheses around that. We just plugged in to our function. Now what?
Hey, why are you adding that?
All I'm doing is I'm
Oh,
rewriting this formula, but in the place of t, I'm substituting x to the power
I
of 3.
thought you were doing the second part already.
Yeah, okay. I'm going to multiply. So I just wrote f of v. What do I write now? Times something. What is it, Stego? Say it louder. So it's this thing, yeah, the derivative of x to the power of 3. What is the derivative of x to the power of 3? Yeah, times 3x squared. Okay, that's the first part of the formula. We just wrote down this f of v times v prime. Now we say, okay, subtract this stuff. So we plug in 23 to each of these. But before we do all that, what is u prime? What is the derivative of 23 that we're going to be multiplying by?
0.
0. So we don't have to do any of that. Done. That's our final answer. Let's try example number 2. All right, Gio, help us plug in. Go.
2 parentheses 2x to the fourth. Everything to the third minus 2x to the fourth.
Perfect. All of that.
All of that multiplied by 8x squared to the third. No, yeah.
8x cubed.
The third, yeah.
Perfect. You have the first half of it. Arrow, talk to us about the second half.
E's not a variable, right?
Nope. E is a number.
E is a number, which means the second half doesn't matter.
Yep, minus 0. Because, yeah, E, again, is just a constant. Done. There's our final answer. Box it.
Is this like what's going to be in the homework?
These example 1, 2, and 3, no. Because the homework is meant for AB calculus. So as long as you, I don't know how often it comes up in the test, so I don't know if I should make you do this, but I just want you to at least see it once. The homework that you're going to be doing is very, very easy. This example 3, you're going to be doing in the homework over and over again. Example 1 and 2 are the way too hard. I just want to give you a glimpse of what the true fundamental...
1 and 2 are hard.
1 and 2 are too hard. 3 is what you're going to be doing in the homework over and over. Let's try 3. So what am I going to do?
Plug in x
So 5 times
x
x
plus
plus 1. Okay, all that's going to be multiplied by
1.
1. So there it is. That's what you're going to be doing for the homework over and over. Although with the graph, so I guess a little bit harder, but there it is.
That's it.
That's, yeah, so it's the second fundamental theorem of calculus is easy if this is just x, right? Because the derivative is 1, this is just a constant term. It looks really nice. Cool. So I think you guys got a good handle on it. Give me a fist of 5 on our objective today. How well can you determine what's happening when you take the, well, I guess I didn't do a good job of talking about the graph part of it, so maybe only a 4 maximum. But in terms of understanding this second fundamental theorem of calculus, how well do you understand that, guys? So 3, 4, 4, 4. Is that a 4? 3, 3? Okay.